We want to understand the purpose of the scientific method. We want to know the difference between qualitative and quantitative observations. We want to be able to describe the difference between hypotheses, theories, and models. And so what is a scientific method? It's a logical approach to solving problems by observing and collecting data, formulating hypotheses, testing hypotheses, and formulating theories that are supported by the data. This is a step-by-step process, guys, that all scientists use. And it is important to recognize that it is a step-by-step process. It's important to recognize that it actually has to be done in the correct order for it to be the scientific method and to do what it is that we desire the scientific method to do and provide for us. So what are these steps? We start with observations. We start by making observations. We cannot do the scientific method. We cannot formulate hypotheses out of thin air. Okay, so observations are basically using the senses to get information. And the information that we collect is called data. And data can fall under two categories. It can be qualitative, it can be quantitative. Qualitative data is descriptive. We can talk about the color of what we're looking at. We can talk about whether it's a solid or a liquid or a gas, but it's definitely descriptive. Quantitative is numerical. Quantitative data is specifically connected to ultimately the measurements that we are making, the measurements that we are taking, and that gives us numerical data that is called quantitative. Okay, everything that we're studying, the definition here is a specific portion of matter in a given region of space that has been selected for study during an experiment or observation. What we are looking at, what we are studying, what we are observing, what we are collecting data on, this is called a system, and we talk about these things in science in terms of the system that we're looking at. We move from our observation making to actually formulating a hypothesis. And our book here is going to define a hypothesis in terms of making generalizations about the data and then moving from generalizations to formulate a hypothesis or a testable statement. And the book is going to tell us that a hypothesis very often is an if-then statement. I want to actually go a little bit deeper on this, guys. A properly understood hypothesis is a logical explanation of the observations we've made. We make observations, and then can we explain what those observations are? And a logical explanation of what we observed is a better understanding of what a hypothesis is. Then we need to be able to make a prediction, and very often the prediction, which is not the same thing as the hypothesis, because the hypothesis is an explanation. The prediction based in the hypothesis is usually an if-then statement. And this is what we use, our hypothesis and our prediction. They need to be very logical. They need to be worded very tightly, because then we move on to an understanding of how we can test our hypothesis based on the prediction. So I want you to understand those subtle differences, guys. And how we test the hypothesis is actually conceptually us now moving into the experimental phase. And what we do is we actually design experiments that will allow us to collect the data based on the prediction that we made, recognizing that the prediction is based on the hypothesis. And this will then ultimately help us to be able to support or refute the hypothesis or the theory that we're talking about. And a good experiment needs to have controls and variables. And the controls are conditions in the experiment that always remain the same, always remain constant, whereas the variables are experimental conditions that change. And in fact, the variables should be the specific things that you're testing in terms of your your prediction and your hypothesis. And in fact, you should try to design an experiment such that you have it limited so that you're only testing one variable at a time, so that you can actually look for and identify cause and effect relationships. And moving on to theorizing, once you've collected data as you've run your experiment, we create what we call models. Models in science are not just physical objects, but models are explanations, or they're diagrams, they're ways of understanding phenomenon or the relationship between data and events. Models can be visual, they can be verbal, they can be diagrammatic, they can be mathematical. Okay, an atomic model of matter, what I referred to in the first chapter as the particle theory of matter, it's just that, it's an explanation and understanding of matter based on the fact that it's made out of atoms. Okay, from our working out these models, okay, then we move into a theory, which is a broad generalization that explains the model or the body of facts or the phenomenon. It explains everything that we've been able to find and then write up. And an example of a theory would be the atomic theory. That is the theory of how atoms are actually made. Okay, what makes up atoms? And again, we find that based on our model, which is based on the data we collected, explaining from our experiments the different hypothesis we had and the predictions that came from that hypothesis. And all of this follows quite clearly here. All this follows from this flowchart where you see we have observations being made, and those observations are going to lead to the formulating of a hypothesis, which will classify. They'll be predicting, and that leads to testing. And if the testing creates data that doesn't support the hypothesis, notice you move back to your hypothesis and you rework it. If the testing does, and you move on to theorizing, where you're constructing models and you're communicating, even making more predictions, ultimately publishing your results, which is communication, which then, if you see back, leads back to more testing, and that testing being more scientists from around the world who now have this information, working on trying to confirm what you've done and what you have found. All right, now we're going to look at the units of measurement. And here, what I want you guys to be able to do is distinguish between a quantity, a unit, and a measurement standard. We're going to be able to name and use the international standard units for length, mass, time, volume, and density. We're going to distinguish between mass and weight, something that we've already done a bit. And we're going to look at density calculations. And we're going to transform a statement of equality into a conversion factor. And this is all, now we're kind of getting into the heart and soul of the types of problems you're going to do in chemistry. You're going to need to be able to do these and apply all of these properly and appropriately. Units of measure. It's important to remember, guys, here, measurements represent quantities, but they are not quantities. A quantity is something that has a magnitude, size, or amount. So you've got to understand, it's a subtle difference, but it is there. When we measure something, we're representing the quantity, but we're not actually giving the quantity. Okay, so measurements and quantities are not the same thing. Teaspoon is a unit of measurement. Okay, volume is a particular number, which is a quantity. And how you choose and use your units is going to depend on the quantities that you are measuring. So SI stands for International Standard. Basically, the French is there if you know how to pronounce it. I'm not going to try to pronounce it here. I wouldn't want that to be recorded because I'm sure it's going to sound awful. But it's the standard that all scientists use around the world. So those of us in this class who are Americans, we're going to have to start moving away from the English system of measurement and start thinking a little bit more broadly, seeing how what we're studying is science. Okay, and there are 7 base units. And then all the other units are mostly going to be derived from those 7. So let's take a look at those. Here they are. Length, symbol is lowercase l. abbreviation is M for meter. Mass symbol is lowercase m, abbreviation is kg for kilogram. Time symbol is lowercase t, abbreviation is s for second. Temperature symbol is uppercase T, abbreviation is K for Kelvin. Amount of substance, the abbreviation or the symbol is N, the abbreviation is MOL for mole. Electric current, ampere, you see that as A, and luminous intensity, candela, CD. We won't deal with electric current and luminosity much in this class. Now with mass, it's the measure of the quantity of matter, and the SI standard for mass is the kilogram. Okay, weight is the measure of gravitational pull on matter. So mass does not depend on gravity. Mass is how much stuff is present. Weight is how much gravity is pulling on it. So if I weigh 230 pounds on Earth, I weigh considerably less than that on the moon, and I weigh considerably more than that on Jupiter. Okay, but if I have 5 grams of some substance, if I have 5 grams of soil, it is 5 grams on the Earth, it is 5 grams on the moon, it is 5 grams on Jupiter. It doesn't change. Doesn't have anything to do with gravity. It's just the amount of stuff that is present. So it's important that you know that difference. Basically, in chemistry and in science classes, you're going to deal with the mass and not the weight so much. Although in physics, you would deal with the weight a little bit more, I would think, but possibly not. Everything is really going to be talking about mass. Length. Length is a measure of distance. The SI standard for length is the meter. The kilometer is used to express longer distances. A centimeter is used to express shorter distances. Again, you need to know these. Now we can derive units. We can talk about area, volume, density, molar mass, molar volume. Probably won't deal with energy much. But these are derived because they're a combination of one sort or another of two other ones. So area is length times width. So the unit is meter squared or square meter. Okay, volume is length times width times height. So now you're talking about cubic meter. Density is mass over volume. So it's kilogram over cubic meter, or kilograms per cubic meter. Molar mass is mass over amount of substance. So it's kilograms per mole. Molar volume is volume over amount of substance. So it's cubic meters per mole. This is what we mean by derived. These are combinations of SI units. Okay, and then there's pressure, which is measured in kilograms per meter times second squared. That doesn't make sense. I think that's a typo. I'm going to look that up. But pascals is usually what we'll use if we do pressure. And we will talk about pressure in a lot more detail when we get to the gas chapters. All right, volume. Volume is the amount of space occupied by an object. And we said the derived SI unit is cubic meters. We can use the cubic centimeter. But the liter is a non-SI unit. So even though the liter is the metric unit for volume, okay, it's not the scientific standard for volume. So you're going to have to understand conversion, right? If you have 1 liter, it's the same thing as 1,000 cubic centimeters. If you have 1 milliliter, it's the same thing as 1 cubic centimeter. And that's important because we're going to talk about conversion and conversion factors. Density, the ratio of mass to volume, or mass divided by volume, looks like that. There's your formula for density, D equals M over V, mass over volume. And therefore, it's going to be kilograms per cubic meter. That's going to be the derived unit. We can also use grams per cubic centimeter and grams per milliliter. And density is a characteristic physical property of a substance. What we mean by that is the density of a substance will always be the same under the same context or circumstances. We can actually identify unknown substances by figuring out their density. This chart actually gives us known, these are all densities at 20 degrees Celsius or room temperature. Notice copper, it's 8.92. It's always 8.92. If you have some substance and you want to figure out what it is, one of the things we'll do in a chemistry class is we will always determine densities. And then we can look up and we can see, well, I find the substance, it's got a density of 8.92. Very well could be copper. That's what we mean by characteristic physical property. So let's look at our first sample problem. A sample of aluminum metal has a mass of 8.4 grams. The volume of the sample is 3.1 centimeters cubed or cubic centimeters. Calculate the density. So what this looks like, you should write out what you're given is. You're given a mass and you're given a volume. Your unknown, what you're trying to find in this case, is density. Write out your formula, plug it in and play, and do the math. Make sure you keep track of your units. And you get 2.7 grams per cubic centimeter, which is your density. That brings us to a discussion about conversion factors. Okay, these are important. A conversion factor is a ratio derived from the equality between two different units that can be used to convert from one unit to another. An example, how do we understand what that means? Well, quarters and dollars. Okay, we know that they're two different units, but there is an equality. A certain number of quarters equals $1, okay, and vice versa. And we can write those equalities out. 4 quarters equals $1. So 4 quarters over $1 equals 1. $1 over 4 quarters equals 1. We also can write it out. $0.25 over 1 quarter equals 1. And 1 quarter over $0.25 equals 1. By understanding that equality, we can then create these factors that will allow us to convert. And you're going to take this concept, guys, and you're going to apply it to your problems in chemistry, because you cannot work problems with different units. You cannot multiply kilograms and grams. Okay, you've got to be able to convert. You always have to be working apples to apples, oranges to oranges. Always. This leads us from conversion factors to dimensional analysis, which is a mathematical technique that allows you to use units to solve problems involving measurements. How do we do this? We start with the quantity sought, and the quantity sought will always equal the quantity given times the conversion factor. That's dimensional analysis by definition. If we stick with our examples of quarters, we can do an example, the number of quarters in $12. Well, you have to do a dimensional analysis problem. The number of quarters equals $12 times the conversion factor. What's your conversion factor? What do you want to do? You want your answer in quarters. And this is the rule that you should always apply. You want your answer in quarters, so you need to set it up to get rid of the dollars. So your conversion factor is going to be 4 quarters over the dollar, because you've got dollars on the top, dollars on the bottom. They cancel out. 12 times 4 quarters is 48 quarters. You can set up every chemistry problem the same way, and you will be expected to. This chart shows you in more scientific terms, how do we use conversion factors? Well, identify the quantity and unit given and the unit that you want to convert to. Okay? So, number 1, your quantity and unit given, you've got 4.5 kilograms. You want your mass in grams. You figure out the equality that relates to the two units, which is kilograms to grams. You set up your conversion factor so that you cancel out the given unit and leave the unit you want. So in this case, it's 1,000 grams over 1 kilogram, so that you have kilograms on the top and kilograms on the bottom. They cancel out. Then you multiply and you carry your unit over to the answer. And so 4.5 times 1,000 is 4,500. You carried your unit over. It's grams. We can also derive conversion factors if we need to know the relationship between the unit you have and the unit you want. So what are the conversion factors for meters and decimeters? You just need to know the relationship. 1 meter equals 10 decimeters, which is the same as saying 0.1 meter equals 1 decimeter, which is the same as saying 10 decimeters equals 1 meter. And what you put on top and what you put on bottom is strictly a function of which unit you want to cancel and get rid of and which unit you want left in your answer. This chart is in your book, and it shows the relationships, remembering the basic unit, meter, seconds, ampere, mole, candela. Okay, and these are just prefixes that will show you, you can see where the different relationships are, from giga to mega to kilo to centi to milli to micro to nano to pico. Everything's going to be based on 10, so everything is related, and your conversion factors will be based on that as well. So here's another sample problem. Express a mass of 5.712 grams in milligrams and in kilograms. So here you have, that's what you're given. You want to get the mass in milligrams and kilograms. Let's solve it for milligrams first. We know that 1 gram equals 1,000 milligrams, which means you can have one or the other on top. You need to decide which one you're going to have on top based on which unit you want to cancel out and which unit you want to have at the end of the problem in your answer. In this case, you want grams on the bottom because you want to get rid of grams. You set it up, 5.712 grams times 1,000 milligrams over grams. Your 2 grams cancel, meaning your answer is going to be in milligrams. You do the math, 5,712 milligrams. We set it up again, start out the same way. This time you want to solve for kilograms. You know that 1,000 grams equals 1 kilogram. You know that you're either going to have it set up one way or the other, depending on what you want to get rid of. You're going to pick again with the grams on the bottom, because that's what you want to get rid of. You set up the problem, 5.712 kilograms times 1 kilogram over 1,000 grams. Notice again your grams cancel out, your kilograms carries over into the answer. You do your math, which ultimately this time is going to be 5.712 divided by 1,000, and you get your answer. All right, guys, we are going to start taking a look at the third section of Chapter 2 and try to round this out. We're going to distinguish between accuracy and precision. We're going to determine the number of significant figures and measurements and learn about the rules in using significant figures and performing mathematical operations involving significant figures. We're going to convert measurements into scientific notation, and then very, very briefly just distinguish between inversely and directly proportional relationships. So when we talk about accuracy and precision, one of the examples I like to use is an bow and arrow shooting at an archery target, or you could talk about a rifle shooting at a rifle target. Accuracy refers to the closeness of the measurements to the correct or accepted value of the quantity measured. Okay, so that is your shots are getting in the bullseye, so to speak. Precision refers to the closeness of a set of measurements of the same quantity made in the same way. So that is, your shots are all close together. So accuracy is your shots hit what you're aiming at. Precision is your shots are all close together. And we've got a diagram that will explain this further. These are dartboards, okay? And the first one, you see all the darts are in the bullseye and all the darts are close together. So that's high accuracy and high precision. And the second one, none of the darts are in the bullseye, but they're all still close together. So that's low accuracy and high precision. And the third one, we notice that none of the darts are in the bullseye and none of them are close together. And that is low accuracy and low precision. Now, when we talk about making measurements, we talk about accuracy and precision, we talk about calculating percentage error. Okay, this is nothing that you're going to be doing in the first several labs, but you will eventually get to this. We define percent error calculated by subtracting the accepted value from the experimental value, dividing the difference by the accepted value, and then multiplying by 100. So what that looks like here is an equation or formula form. Is experimental value minus accepted value divided by accepted value times 100. What this looks like in terms of a problem, if you have a student who measures the mass and volume of a substance and calculates its density as 1.40 grams per milliliter, and we know that the accepted value of the density is 1.30 grams per milliliter, you can determine the percent error of the student's measurements. We do this by using the formula and then just plugging everything in. And that will end up looking like 1.40 grams per milliliter minus 1.30 grams per milliliter divided by 1.30 grams per milliliter times 100. And in this case, the percentage error, or the percent error, is 7.7%. Now we also have to recognize that making measurements in a lab is a skill, and it involves not only humans, but it involves instruments, all of which will introduce error and uncertainty, which will exist in the measurements. And so first, it's a skill. You are not going to be as good at making measurements now as you will be in the future after you make a lot of measurements. So it's something that can be learned and practiced. The conditions of making your measurements. If you're measuring something that tends to absorb moisture and it's a very humid day, that's going to change the measurements that you make. And then the measuring instruments. Some instruments are more precise than other instruments. And our use of significant figures helps us to understand the precision of the measurement and the precision of the instrument used to make the measurement. So when we look at significant figures, we have rules, and we apply these rules in every single case every time we do a problem. Significant figures in a measurement consist of all the digits known with certainty plus one final digit which is somewhat uncertain or is estimated. The term significant does not mean certain. So significant has nothing to do with certainty, it has to do with precision. You can look at this in terms of measuring this nail on a ruler in centimeters. You're going to look at where you're at, you count your 6, and then 1, 2, 3, and then you can estimate that last digit and get 6.35. Here are the rules, and you're going to need to know these because, again, significant figures are going to apply to every problem you do. First, zeros appearing between non-zero digits are significant. Second, zeros appearing in front of all non-zero digits are not significant. Third, zeros at the end of a number and to the right of a decimal point are significant. 4, zeros at the end of a number but to the left of a decimal point may not, left of the decimal point or may not be significant. If a zero has not been measured or estimated but is just a placeholder, it is not significant. A decimal point placed after zeros indicates that they are significant. We can look at these in terms of these problems. How does it play out? Take a look at these and we'll try to understand each one. With 28.6, there are no zeros. All three digits are significant. 3,440 with the decimal point. By Rule 4, the zero is significant because it is immediately followed by a decimal point. There are 4 significant figures. 910 meters. By Rule 4, the zero is not significant. There are 2 significant figures. In this case, by Rule 2, the first 2 zeros are not significant. By Rule 1, the third zero is significant. So there are 4 significant figures. By Rule 2, the first 3 zeros are not significant. By Rule 3, the last 3 zeros are significant, so there are 5 significant figures in this case. Now, when we do rounding, you've got these rules here. If the digit following the last digit is to be retained is greater than 5, you should increase by 1. If it's less than 5, you should stay the same. If it's a 5 followed by a non-zero digit, increase by 1. If it's 5 followed by non-zero digits and preceded by an odd digit, you increase by 1. If it's 5 not followed by a non-zero digit and the preceding significant digit is even, you stay the same. Those are rules for rounding. They're pretty complex. What I tell you guys is simply this. If you round the way you have been rounding ever since you were taught rounding in elementary school, you're pretty much going to get everything correct in terms of rounding. All right, how do we do arithmetic or mathematical processes in terms of significant figures? In addition or subtraction, the significant figures. Okay, when adding or subtracting decimals, the answer must have the same number of digits to the right of the decimal point as there are in the measurement having the fewest digits to the right of the decimal point. Now, in multiplication and division, this should say multiplication and division here. For multiplication and division, the answer can have no more significant figures than are in the measurement, the fewest number of significant figures. The point here, guys, is that when doing problems, your answer cannot be precise than the number in the problem with the least amount of precision. That's the principle. Now, these two things explain it specifically, but the principle is that your answer cannot be more precise than the number in the problem with the least amount of precision. So what does this look like? We're going to carry out these calculations, following the rules for correct significant figures. 5.44 meters minus 2.613 meters. 2.4 grams per milliliter times 15.82 milliliters. What does this look like? In the first one, you do it. Now your answer would appropriately and properly be 2.84. There should be 2 digits to the right of the decimal point to match the 5.44 meters. In the second one, your answer would appropriately be 38 grams. There should be 2 significant figures in the answer to match the 2.4 grams per milliliter. Now, how we do conversion factors with significant figures, all that you need to know here is that you don't generally have to worry about significant figures with your conversion factors because most conversion factors are defined quantities. So it doesn't really apply to conversion factors. Now, in terms of scientific notation. In scientific notation, numbers are written in the form of m times 10 to the nth power, where the factor m is a number greater than or equal to 1 but less than 10, and n is a whole number. Now, what we see in the example here is you have this number 0.00012 millimeters, which equals, when converted into scientific notation, 1.2 times 10 to the negative 4 millimeters. The idea with scientific notation, guys, is to be able to take very large numbers that are very big and small numbers that are very big and write them in a more manageable way. Again, large numbers that are very big and small numbers that are very big and write them in a manageable way. In this case, what we did was, 0.00012 would be a small number that's very big. Okay, and what we did there was we moved the decimal point 4 places to the right and multiplied the number by 10 to the negative 4. Well, why did we do 10 to the negative 4? Here's the rule. You determine m by moving the decimal point in the original number to the left or right so that only one non-zero digit remains to the left of the decimal point. And then you determine n by counting the number of places that you moved the decimal point. If you moved it to the left, n is positive. If you moved it to the right, n is negative. Now, how do we do our mathematical operations using scientific notation? Because you will have to do that. First, with addition and subtraction, these operations can be performed only if the values have the same exponent. Your n factor has to be the same. So 4.2 times 10 to the 4 kilograms plus 7.9 times 10 to the 3 kilograms cannot be added as they are. Again, this brings us back to the apples to apples, oranges to oranges analogy. You can convert everything so that it's times 10 to the 4, so that 7.9 times 10 to the 3 would be converted to 0.79 times 10 to the 4. Then you add and you round. Or you can make sure everything's 10 to the 3. So at this point, your 4.2 times 10 to the 4 is converted to 42 times 10 to the 3. You add, and then you put it back into scientific notation, and you round. Multiplication is different. The factors are multiplied and the exponents are added algebraically. So if you start with 5.23 times 10 to the 6 micrometers times 7.1 times 10 to the negative 2 micrometers, you're going to do it algebraically. What does algebraically mean? Well, you do your two numbers, 5.23 times 7.1, and you then do 10 to the 6th times 10 to the minus 2. That gives you 37.133, and when you multiply your exponents, you know you just are adding them, so 6 plus negative 2 is 4, and you have to remember that you multiplied micrometers, so now that's micrometers squared, and then you need to convert it into proper scientific notation, and so you move the decimal point appropriately, and what you get is 3.7 times 10 to the 5 micrometers. We also can do division. In division with scientific notation, the m factors are divided, and the exponent of the denominator is subtracted from that of the numerator. So you have 5.44 times 10 to the 7 grams, divide by 8.1 times 10 to the 4 moles. 5.44 divided by 8.1 times 10 to the 7 minus 4 grams per mole, and that becomes what you see there, and then you convert it into proper scientific notation, and it becomes 6.7 times 10 to the 2 grams per mole. Now, how you do sample problems, guys, lots of problems in chemistry, okay? You know, on some level, I could say, look, I don't care how you do them, as long as the answer's right, but I've learned too much in my own doing of chemistry problems and my own teaching of chemistry that very seldom does that work for the student who's working through chemistry. So I do think that there is a proper and appropriate procedure to use in doing the problems. The first step in solving a quantitative word problem is to read the problem carefully. Read it as many times as you need to analyze the information and gather the information out of it. Then plan. Once you understand what you're given and what it's asking for, then you develop a plan for solving the problem. And then you compute, okay? Once you have all that laid out, you basically do the math, substituting the data and the necessary conversion factors into the plan you have developed. Then you evaluate. You examine your answer to determine whether it is reasonable. Lots of ways you can do that. Always check to make sure the units are correct. Technically, with dimensional analysis and units, you should be solving for your units first anyway. You should know what your units are going to be in the answer, and you should set up the problem so that your units are correct. And then you make an estimate of the expected answer. That can be a way to evaluate. You can check the order of magnitude. And then make sure that your answer expressed is using the rules for significant figures and is properly in scientific notation if appropriate. So what does this look like in a problem? Let's say you've got to calculate the volume of a sample of aluminum that has a mass of 3.057 kilograms. The density of aluminum is 2.70 grams per cubic centimeter. First, we're going to analyze. We know that we have given the mass in kilograms, the density we have given in grams per cubic centimeter. We should note at this point that we have kilograms and grams. So that's going to be a problem where there's needed conversion. And we have our unknown. We want to find the volume of aluminum. When we plan, we note again the density unit is grams per cubic centimeter. The mass unit is kilograms. So we're going to need to use a conversion factor. 1,000 grams equals 1 kilogram. And then we take the density equation and rearrange it to solve for volume. D equals M over V, which also equals V, or volume equals M over D. Now we compute. Computing is simply doing the math. So you plug in 3.057 kilograms over 2.70 grams per cubic centimeter times your conversion factor, which would be 1,000 grams over kilograms. That has you set up to get rid of the unwanted units. You cancel out grams, you cancel out kilograms, you're going to have an answer in cubic centimeters, which is SI for volume. You do your calculator answer, which is 1,132.222 cubic centimeters. You round your answer to 3 significant figures according to the rules and put that into scientific notation. And you get 1.13 times 10 to the 3rd cubic centimeters. Now you evaluate what you did. You have your answer. You make sure the unit of volume is correct. You can do an order of magnitude to estimate what the correct answer should be over. And you can double check the correct number of significant figures and make sure that your scientific notation is appropriate. Now finally, in this chapter, we look at direct proportions and inverse proportions. We say that two quantities are directly proportional to each other if dividing one by the other gives a constant value. We read that notation this way: y is proportional to x. What that looks like, well, in terms of mass versus volume for aluminum, which is density, right? Every time you have a mass of aluminum divided by a volume of aluminum, you're going to get m over v, or a density of near 2.7, regardless of what your mass and your volume is. So if you plot those masses and those volumes, okay, on here, and then you plot where you're at, notice you end up getting a straight upwardly arced diagonal line. That is what you would expect to see in a direct proportion. In inverse proportions, two quantities are inversely proportional to each other if their product is constant. So we read that y is proportional to 1 divided by x. And what that looks like here, guys, is, again, your constant in terms of pressure volume. Notice over on the right hand column, pressure volume, you're always getting an answer of around 50. Okay, and that graph for an inverse proportion is going to look like the red line there. Okay, this is covering everything in chapter 2. You guys, it's very important that you remember you're going to start looking at problems, and the problems are going to get more and more complex. There's going to be lots more need for conversion factors and use of conversion factors, so on and so forth. What I would suggest, guys, is that you take each of your problems one step at a time. Okay, work them one step at a time and break them down into simple steps. Don't get overwhelmed, because it's not overwhelming if you break it down into steps. Don't get overwhelmed. Work it, and when you have trouble, ask, and we can go over them in class. Keep studying hard. Keep working hard.